My name is Wang Yunchao. Today I want to introduce my poster, Evaluation Criterion for Visual Cryptography Schemes via Neural Network to you. First, what is a visual cryptography? Visual cryptography is to distribute a secret image to different shares so that the original secret information cannot be recovered without the cooperation of several shares. Moreover, each share is kept secret to the others. Next, I'd like to introduce why the visual cryptography scheme needs to be evaluated. It is difficult to evaluate the security and the performance of visual cryptography schemes for grayscale and color informations. Firstly, when some visual cryptography schemes are used to divide an image into shares, there's no guarantee that the each share would not reveal information about the original image. Secondly, it is hard to determine if one can always derive the same information from the original and the recovered image. If the recovered image cannot convey the key information as the original image, then the encryption will be meaningless. Then I'll introduce visual cryptography schemes. Firstly, a host scheme. This figure shows a host cryptography scheme for color information image. This scheme uses color decomposition to derive a color image into three primary colors: yellow, magenta, and cyan. Then use the Haftel technology to get three different shares. Finally, stoke these three shares to recover the image. Comparing to host scheme, Nakajima and Yamaguchi scheme is different. Besides original image, this scheme takes two other images as containers. For hiding secret shares, an encrypted image is generated by combining a container and a piece of information from the original image. Then decryption is done by stoking the two shares together. Then I'd like to explain our criterion to evaluate the scheme. First, I'll introduce encryption inconsistency. Through the neural network, we can get the level of the original image R. Use label R to denote this. Meanwhile, we can get the level of shares denoted as label S by comparing label S with label R. The encryption inconsistency between shares and the original image is defined as follow. Then it's about decryption consistency. Through the neural network, we can get the level of recovered image denoted as label M. By comparing label M with label R, the decryption consistency between the recovered and the original image can be defined as follow. After introducing two criterion, I'll talk about how to adopt inconsistency and consistency for schemes. I take host scheme as an example. We randomly selected 20 images from the ImageNet dataset and performed host scheme on these 20 images. We obtained three shares and one recovered images corresponding to each original image. Then, via neural network, we get the levels of all the shares, the recovered image, and the original image. By comparing the obtained levels, one can easily derive the encryption inconsistency. Furthermore, the decryption consistency can be obtained. This figure shows how to calculate the inconsistency of the host schemes. This table presents the inconsistency and the consistency in host scheme. From the result, we observe that with the identification of three different CNN, VGG16, VGG19, ResNet15, the inconsistency of shares and the original image is as high as 100%, which means the shares can conceal the information of the original image very well. However, the consistency of recovered image and the original image is zero, which also means that the recovered image is quite different from the original image.